a great honor for me to give a talk here for the Sunda Festa. And I also would like to thank Sunda, Vijay, and others for giving me this opportunity of giving a series of lectures. And I hope it was okay for you. So, the title of my talk is Group, Subgroup, Subfactors Revisited. And the reason for this word revisited is that actually I worked on this subject in my master thesis. And from time to time I came back to this subject. So that's why the reason of the word. That's the reason of the word. So first of all, before going to mathematics, can you see it? Okay. I put some Japanese words here. Oh, you read it. You can read it. Okay. So this word, this is one word, is in Japanese. So it means 60th birthday. We have a particular word for 60th birthday, and it consists of two Chinese characters. And first character is ring, means ring. So when in Japanese, von Neumann algebra is von Neumann ring, von Neumann kan. It's called kan. Okay. And second letter is reki. We say so. This is kan reki, and it means calendar. So it's a, so to speak, ring calendar. But the real meaning is that so in Japan, I think actually in China probably. So we have two way of counting numbers. In one way, the unit is 10. Like everywhere in the world. So in one way it's 10, the unit is 10, and in the other way, the unit is 12. So 60 is the smallest common multiple. So it means you came back. You came back to the original point. So yesterday you came back to the original point. So today you start the next cycle of 60 years. Okay. And this is just a congratulations. And this is Sunda in Japanese. So happy birthday. Right. So I start mathematics. So since Srinivasan already gave the definition of von Neumann algebras to one factor, so let me go very quickly. So all right. H is a Hilbert space. And M is a subset of B of H. B of H is the set of bounded operators on N, H. And then a subset M is for the von Neumann algebra. M satisfies the following three conditions. First of all, it's closed under star operation. So X star is adjoint operator of X. And M is an algebra under natural operation of addition and multiplication and so on. And it is closed in weak operator topology. So this is the definition of a von Neumann algebra. Then a von Neumann algebra is called a factor if it's center. So this is center. Center of M is trivial, the complex numbers. And then a factor M is of type 2-1 if it is an infinite dimensional and there exists a so-called tracer state. So tau is a trace. We call it trace. And it is a linear functional satisfying this trace condition and this normalizing condition. So this is a 2-1 factor. But you already saw it in Srinivasan's talk. Okay. So we think of actually two 2-1 factors. So one N is a 2-1 factor, and inside M, which is again 2-1 factor. We consider this situation. Then Von Jones introduced a notional index for 2-1 factor. So namely, the index of N inside M is this number. It's doesn't explain anything, but it's, so to speak, the relative dimension of M to N. Well, more precisely, so 2-1 factor is a very nice notion of dimension. So every, say, N module, for every N module, you can assign a nice dimension, so relative dimension, a positive number. So essentially, this number measures how many N is contained in M as a left N module. So N is subalgebra of M. So M is naturally, so by left multiplication, M is left n module. So this essentially counts the number of n contained in M. Then Jones shows the following very striking result. So this number, belongs to, well, either this discrete series set or continuous series. So, well, from just this definition, then you never expect this kind of thing. But it's, well, he showed it. So this is really a mysterious 7. But today, I'm not talking about this mysterious discrete series, but I'm talking about subfactors of integer index indices. So, namely, so I only talk about so-called group, subgroup, subfactors. So R is a 2-1 factor. Throughout my talk, R is a 2-1 factor. If you like, you can assume that it's a hyperfinite 2-1 factor. And Z is a finite group, and H is its subgroup. Then we consider G action on R. And let's assume it's outer. Don't worry about this word. So it's some technical condition. So assuring that cross product is again a factor. Now, given an action, G action alpha on R, you can construct called a cross product. It's as this factor. So for G and H, then you can consider this pair. The cross product of R by G action and R by H action. Then the notion of index is such a natural thing that you get this equation. So the index of this group, subgroup, subfactor is the same as the index of H in G. So this shows that this notion of index, Jones' notion of index, is very natural. Right. So this is a group, subgroup, subfactor. So I concentrate on this particular family, this particular subfactor. Right. So let me make one observation. So if there is a normal subgroup of G, non-trivial, and it is contained in H, then so the group, subgroup, subfactor forgets the information of K. Namely, it carries only the information of G over K and H over K. So here, P is a cross product of R by K. So the group, subgroup, subfactor forgets the information of K. So let's make this assumption. Assume there is no such case. Throughout my talk, I make this assumption. So this is not really a trivial fact, but it's a consequence of kind of, say, a took homology vanishing in a non-commutative sense. So let's make this assumption. Then the natural question is the following. Does the group, subgroup, subfactor uniquely recover the original pair? So does this remember the original pair? That's a very natural question. But a bit surprising. So the answer is no. And actually, the first counterexample was provided by Sundar and Kodia in 2000. So in this paper, Kodia and Sundar, the subgroup subfactor, mass conjugate. So they came up with this counterexample, where the larger group G is a symmetric group of degree 4. So let's consider two subgroups. The first group 8 is the subgroup generated by this permutation. So it's isomorphic to Z over 4Z. The next group is this. So it's the subgroup generated by these two permutations. Then it's isomorphic to Z over 2 times Z over 2. Then they show that these two pairs, so H in G and K in G, give rise to isomorphic subfactors. So this means that in general, the group subgroup subfactors cannot recover the original pair completely. And what they did is that they computed so-called connection. So there is in a good situation, there is a complete invariant for subfactors, namely the Okunyan's connection. So for this, then for group subgroup subfactors, there is a way to compute connections by using a representation theory, and they computed. Then they show that for these two, so H and G and K and G give the same invariance. That they proved the theorem. Actually, I wanted to ask you that how you found this example.
The smallest example you can have.
Yeah, this example. Yes.
It is the smallest example you can have.
Okay, so it's the smallest example you can have, but how did you find it?
Everything smaller did not give a counterexample.
Okay.
So, and in some of the lists, this was the first example where which also given some like automated. I don't remember, as you see, a long time ago.
Right. So when I saw this result, I was a bit puzzled because before this result, I had an attempt to show that group subgroup subfactor recovers original pair completely. Actually, I formulated an equivalent problem, but I couldn't solve the problem. But it is natural because there is a counterexample. So after this result came up, so I thought that there must be a very interesting algebra behind this phenomenon. And indeed, there was. So that's how I'm reporting today. So before explaining actually I completely characterize isomorphic group subgroup subfactors. So before explaining that result, I need to show you the invariant for subfactors. So let's get back to the general situation. So M and N are just finite index subfactors. Then starting from this, you can think of various bimodules. So let iota be a M as Mn bimodule. So left multiplication of M and right multiplication of N. And let iota be M as N bimodule. Left multiplication of N and right multiplication of N. So these are fundamental bimodules. And starting from iota and iota bar, you can form various tensor products over M or N. Okay? So namely, so you can think of a tensor product of iota and iota bar over N. Then it turns out that it's not irreducible, but it is decomposed into finitely many irreducible components. So you decompose it. Then again, you take tensor product with iota over M. Then it's not irreducible. You decompose it, and you do that procedure. So you consider every possible tensor product either over N or M, starting from iota and iota. Then you get say Mn, 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 Nm, and N bimodules. And this is not really a tensor category because you cannot make a tensor product of say Mn bimodule and Mn bimodule. But if you choose the right legs, then you can make tensor product. So it's a kind of tensor categories, and this category has two units. Namely, so M as Mn bimodules and N as Nn bimodule. So it has two units. And this category gives in a nice situation, then this category gives a complete information of the subfactor. So, but we need a more handy invariance. So, namely, so in this level, you put all the irreducible Mn bimodules here. Okay. So in this example, you have only 3 irreducible bimodules. And in this level, you put all the irreducible Mn bimodules. In this example, you have only 2. Then you draw a graph. Namely, so if you take tensor product of rho and the iota over M, then it is decomposed into iota and kappa. So with multiplicity 1. So in this example, you put just one line. According to the multiplicity, you put lines here. Okay? In this way, and also starting from, say, kappa, you take tensor product with iota bar over n. Then it is decomposed into rho and alpha with multiplicity 1. So you put one line here, one line here. So in this way, you can draw a graph. Okay? And this graph is so-called the induction and reduction graph. And in fact, they are called the principal graphs. You do the same for here. So you put, okay, in this level, you put all the irreducible element bimodules. Then you draw, okay, induction and reduction graph. Then you get another graph. So in this way, starting from a subfactor, index finite subfactor, you get two graphs, two pairs of graphs, one here and the other here. And they are called principal graphs of the inclusion subfactor. And okay, this notation is not really popular notation, but so this is just for today's purpose. But for some reason, I want to use this particular graph, the graph for mn bimodules and nn bimodules. Let me call this G of, say, curly G, script G of m and n. So in this particular example, you get the same graph for G, these two, and it's a so-called Coxeter graph A5. So this is just a straight line with 5 vertices. Right. So these graphs give you very important information, although they are not completely invariant. So let's get back to the group-subgroup subfactor. So when M and N are group-subgroup subfactors, then for this part, it's easy to, actually the structure of the graph is really easy. So there is a one-to-one correspondence between MM bimodule, irreducible MM bimodule and irreducible representation of G. And similarly, there is a one-to-one correspondence between Mn bimodules, irreducible Mn bimodules, and irreducible representation of H. And the principal graphs are really, this time it's an honest restriction induction graph. Namely, starting from a representation of G, then you can restrict it to H, and you can decompose it to irreducibles. Okay? In a similar way, starting from a representation of H, then you can induce it to the representation of G. Then you can decompose it into irreducibles. Then it turns out that the principal graph, one of the principal graphs for this inclusion is here this induction-reduction graph. But the other principal graph is a bit involved. Namely, it requires the double coset decomposition of Z. So this is a double coset decomposition of Z, and we use this. So G0 is just an identity. Okay? Then we define the subgroup of H this way. Then it turns out that Mn bimodules are parameterized by this disjoint union of the irreducible representation of Hi. Okay? Again, the graph is given by the restriction induction here. So this part is just a disjoint union with the dual of Hi. So let me show you a simple example. So G is a symmetric group of degree 3. H is a symmetric group of degree 2. Okay? So this is a double coset decomposition. So for one graph here, the graph for Mn and Mn, then you have this nice description of the induction and reduction. So it gives you the Coxeter graph A5. And for the other graph, okay, so this H1 is a trivial, so identity group. So the induction-reduction graph is just this part. But remember, so this part is just a disjoint union of the dual of H hat and dual of H and dual of H1. Here, H is this, this is isomorphic to Z over 2Z. Okay, so since this is just an additional copy of H hat, so you have this line and this top. So again, you get Coxeter graph A5 in this example. Okay, this is a way to compute the principal graphs for group, subgroup, subfactor. So, now, so we have a group, subgroup, subfactor. Then, as I explained, there is a one-to-one correspondence between the irreducible MM bimodules and the irreducible representations. But that is not only just a one-to-one correspondence. It is actually equivalence of the tensor categories. So MM bimodules associated to this inclusion is equivalent to the representation category of G as a tensor category, abstract tensor category. So it means that if you have two pairs of groups, say H in G and H prime in G prime, then it means that the representation category of G is equivalent to the representation category of G prime. Okay. So if you know something about, say, duality theorem, Tanaka-Klein duality theorem, or Dobrica-Roberts duality theorem, you must think that, okay, then representation category completely recovers original group, so G must be isomorphic to G prime. You might think that, but it's not really true. To apply the Tanaka-Klein duality theorem, you need to fix this. You need to fix a, say, how to say, okay, realization of vector space realization of the representation category. But this equivalence is in the abstract level. You don't really fix the vector space realization, so-called the fiber function. You don't fix fiber function. And in fact, there is a nice characterization of this situation. It was found by, I think, Geraki, Davidov, and Kosaki and myself independently. So you consider two groups, two finite groups, G and G prime. Then they have an equivalent representation category if and only if, okay, the two groups are related by this relation. I'll explain this in the next slide there, but roughly, so if you start from an abelian normal subgroup and the second cohomology element of the dual of A, and if this class is G invariant, and there is a way to deform this group G. And this situation is completely characterized by this relation. So I'll explain it more. So, let's start with the finite group G. Then let's consider its group algebra. Then it has a nice Hopper algebra structure. Namely, it has a coproduct, so-called coproduct, antipole, co-inverse, and co-unit. So it is a Hopper algebra. And but this is a very special class of Hopper algebra. Namely, so the coproduct is co-commutative. So you can flip the tensor component, you get the same. And it's known that every co-commutative, say, semi-simple Hopper algebra is given by a group algebra. It's well known there. Now, assume you are given a abelian normal subgroup and a cocycle of A hat on A hat with coefficient in the torus group. And assume that the class, cohomology class is G invariant. So G naturally acts on A, so it naturally acts on this cohomology class too. Assume the class is G invariant. But you don't assume that the cocycle itself is a G invariant. So remember, G is a two-variable function of A hat. But the function algebra of A hat is nothing but the group algebra of A by duality. And since A is a subgroup of G, so the group algebra of A is embedded into the group algebra of G. So it means that you can regard omega as an invertible element of this tensor product here. So this formula makes sense. In other words, you can twist the coproduct by using this cocycle. But thanks to this condition, so G invariance condition, this new coproduct, actually, so cocycle relations show that this is again a coproduct. And this invariance condition assures that actually this new coproduct is again co-commutative. So by the structure theorem of co-commutative Hopf algebras, there must be a group, new group, such that this Hopf algebra, so coproduct twisted by omega, is isomorphic to the group algebra of G omega. There must be such a group. And actually, there is a precise description of this group. This group is not necessarily isomorphic to the original group, but it's very similar to the original group. It's an extension of G over A by A. Of course, D itself is an extension of G over A by A, but so this could be a different extension. And the difference from the original extension is described by omega. Not omega itself, but starting from omega, there is some construction to produce cocycle of G over A. Okay, so it's a different extension in general. So here is my characterization. So you consider two pairs of groups, okay, H in G and H prime in G prime. Then the two group, subgroup, subfactors are isomorphic if and only if the following conditions are satisfied. Namely, there is a unique, this is a unique, abelian normal subgroup, and there is a non-degenerate G invariant cocycle, cohomology class. So the cohomology class of omega is G invariant, and moreover, there is a nice lift of the cohomology class such that this is trivial. The restriction of omega to this subgroup is trivial. Then actually it's not only this G omega but also H omega. The deformation of H makes sense in this under this assumption. And this happens if and only if the pair H in G and H prime in G prime are related by this. So this is an if and only if theorem. So it's a complete characterization. And again, so H omega is similar to the original H. It's an extension of H over H intersect H by H intersect H. But it could be a different extension from the original extension. So this is a complete characterization of an isomorphic group, subgroup, subfactor. So here is one remark. So assume that G action on G over H is primitive, meaning that the H is maximally. So in this situation, then it's easy to show that there is no such pair. No such pair. So it shows that if you start with a group subgroup subfactor without any non-trivial intermediate subfactor, then this pair completely recovers the original group subgroup pair. So in a sense, actually in an obvious sense, so the in Kodayamas and Sunda's example, the subgroup is very small, and which allows this kind of phenomenon. So having a complete characterization in our hand, now it's easy to reproduce Sunda and Kodayama example. So let's start with this abelian group, okay? And we form a semi-direct product, okay? And consider this subgroup. So it's isomorphic to Z over 2n and Z over 2n. Okay? So since this is an abelian group, so by fixing a root of unity, then you can identify A and A hat, okay? And consider this cocycle. Then this cocycle satisfies the previous condition. And you can compute the deformation of H by this cocycle. Then it turns out that it's not isomorphic to the original one. Okay. So you have it extra one here and this is minus 1. So when n is 1, then it turns out that G and G omega are isomorphic to the symmetric group of degree 4. And one by definition H is isomorphic to Z2 cross Z2. But so H omega is isomorphic to Z over 4Z. So this recovers Kodayamas and Sunda's example. So when n is larger than 1, strictly larger than 1, then even the larger groups are not isomorphic. So this way, we get a series of examples. So I have I have just 7 minutes, so at this point I change my topic a little bit and I talk about the Goldman theorem. So let me recall the classical Goldman theorem. So it's a subfactor result before von Jones. So at that time there was no notion of index, but in modern time, so his result is stated in the following way. So it's a characterization of index 2 subfactor. Every subfactor of index 2 is given by the cross product by Z. Right. So this is Goldman result. And there are several ways to generalize Goldman's type theorem. And one way is to give a characterization of cross product, and that's well known. So that's well known, so I'll skip it. But there's another way, namely the characterization of a group subgroup subfactor. Well, you cannot do it in general, but there are some situations which allow complete characterization of a group subgroup subfactor. So I'll talk about it. So let's consider the index 3 case. Okay, assume the index of n is 3. Then there are only 2 possibilities of the principal graph, either A5 or D4. When it is D4, then by the characterization of cross product, so the M is the cross product of n by Z over 3Z actions. So in my master thesis, I proved the following theorem. So assume that n is a subfactor and the principal graph is A5. Then this must be a group subgroup subfactor for this symmetric group pair. So I got this result in my master thesis. So this is a nice situation which allows you to recover group subgroup subfactor. So let me give you a definition of the word Goldman type theorem. So we say that the Goldman type theorem holds for this pair if, whenever you have subfactor whose principal graph is isomorphic to this group subgroup subfactor, the principal graph of the group subgroup subfactor, then so they are actually a group subgroup subfactor. So this is what I mean by Goldman type theorem. So this means that a Goldman type theorem holds for this pair, S2 inside S3. Okay. Then Horn and Zimansky gave a Goldman type theorem in '96. Actually, in their case, the bigger group is a dihedral group over order 4n plus 2, and the smaller group is Z over 2Z. It's not normal. So Horn and Zimansky got this nice Goldman type theorem, and also Horn got this Goldman type theorem. So actually, when I saw their result, I realized that they got a really nice argument. It's fairly better than my proof here. And I look for graphs which allow a similar characterization, and I found this example. So let's assume that the graph is 2 to the n graph, namely, so there is a 1 point at the middle. Then there are n legs of length 2. So for example, this is 2, 2, 2, 2 graph. Okay? Assume the principal graph is 2 to the n. Then something surprising happens. So n must be the prime power minus 1. And actually, so the subfactor is a group subgroup subfactor of this particular pair. So this is a finite field of degree of with p to the a elements. So you regard this as an additive group. Then the multiplicative group of the field act on it naturally. Turns out that this graph completely characterizes this pair. So for example, in this case, the graph is 2, 2, 2, 2. Then so the subfactor is obtained by this pair. Okay. So this is the first infinite series which allows group subgroup subfactor. And we use this result for the complete classification of index 5 subfactors. So this is with Scott Morrison and Noah Snyder. So assume the index of n is 5 and finite depth. Then, so this essentially, so this subfactor is a group subfactor, or it's dual. there is a notion of dual inclusions. So, and all possible pairs of groups are the following. So, cross product like that 5. This is actually this case is covered by von Zimanski, and this is covered by my result. And there are 2 more cases: alternating group case and a symmetric group case. And to prove this theorem, I need to show a Goldman type theorem for this pair. I mean, this alternating group pair. So namely, the principal graph for this group, subgroup, subfactor is so-called 3-3-3-1 graph. There's a 1 bracket here, and then 3 legs of length 3, and there are 1 leg of length 1. So it's 3-3-3-1 graph. So I had to show a Goldman type theorem for this pair, but I generalized a little bit, then I got the following. So assume that the principal graph is 3 to the n1. Okay? Then again, you have a great restriction. N must be prime power minus 1. And the subfactor is actually a group subfactor, and this time the pair H and G are the following. So the larger group is this projective general linear group over the finite field, and H is this diagonal subgroup, upper diagonal subgroup. I think, well, my time is up, so I think I stop here.
When Sn sits in Sn plus 1, then double cosets are true, but they are determined by the constants, when we multiply 2 double cosets. So does that have any impact on your Sn containing Sn plus 1?
A symmetric group case?
Because you illustrated for n equal to 2 and then n equal to 4, isn't it?
Yeah.
Just before this you had
Oh yeah, before this. Actually, I also have a Goldman type theorem for Sn.
S3 containing S2 you are.
Oh, okay.
Sn plus 1 contains Sn.
S3, S4 case, then it gives you the so-called extended E7. And again, you have a Goldman type theorem for that.